Is this better?
Yeah.
Okay. All right. So yeah, is everyone here that could be here? Is everyone here?
Yes, Ratnakar exam now.
Yeah. So I guess we should start, right?
Yeah.
Yeah. Okay. So yeah, I'm sorry for being late. There's not much that I want to talk about. Just like finishing up from last time. We couldn't do it everything in the last session. So yeah. So I'll start screen sharing. Yeah. Right. Yeah. So if you remember, we had this, I had written this sort of pseudocode, right? Um, wait 1 second.
Yeah. Yes.
This. This journal is not, seems like not working for some reason. Sorry. Give me 2 seconds. Okay, I'm having some technical difficulties with the journal thing. Can would you guys mind just giving me 2 seconds? I'll just be like right back. And I think I might need to restart the thing because of some update that has come.
Yeah. Okay. Okay.
Yeah, I'm sorry about this. I'll have to just.
Okay.
Yeah, just stay in the meeting. I'll just rejoin here.
Okay. Sure.
I'm really sorry.
So what happened? Diganta dropped out?
Yes, he said he has some technical difficulties. He said he'll be rejoining.
So he'll be joining back, huh?
Yeah.
Yeah, can you guys hear me? I'm sorry about this. Yeah.
Yes. I can
Yeah.
hear.
Okay. So yeah, it's working now, right?
I made you co-host again.
Yeah. Thanks. Sir. So I don't know why, but I think it was because of some update came and I didn't restart my system. The Wacom was not working. I couldn't write here, so I just had to restart because of that. Yeah. So coming back to this, so if you remember, we had this pseudocode last time, and we had this queue of sort of points that we wanted to block off and use, and we had sort of rewritten the recursive blocking procedure in terms of this queue, and we had made some optimizations, right? So one of the optimizations that we had made was that whenever we see a point, um, like whenever we find that there is a CTI, we try to generalize the CTI in the previous frame to a more general expression, and we do that via this ternary simulation, and then we block the generalized clause that we get from the ternary simulation. So you guys remember this, right? Yes, no?
Yes.
Yeah. Okay. Yeah, and the other sort of optimization that we were talking about was uh, basically when we find that there are no CTIs, then can we derive something more general to block from the fact that the CTI check is returning unsat, right? So that we say that, okay, the CTI check is basically this sort of a check, and since this returns an unsat, we can look at the unsat code of this expression, and we can see that, okay, if the unsat code does not contain x2, that means x2 does not contribute to the fact that this is unsat. So we can directly block x1 and x3 instead, and that will be a more general blocking that is still sound, because you know the fact that x2 is not in the unsat code means that if we just had x1 and x3 here, we would have still got an unsat, right? So we look at the unsat core and we block the clause that we basically, or rather from the clause that we wanted to block initially, we drop everything that is not in the unsat core and block using the resulting clause, which is this s prime over here, right? So do you guys remember this?
Yes. Yes.
Yeah. So are there any questions or anything with respect to that? And can I move on to the next bits?
Yes. And,
Yeah. Okay. So yeah, so there was this other thing that we said, that we are going to use one solver for all of our various checks that we're doing, right?
Yeah.
Yeah, so this solver is going to basically contain, like each frame is essentially is going to have a bunch of clauses, right? All of these clauses are going to go over the same variable, so we don't have different sets of variables for each frame. We have only one single set of variables. Maybe we can have just one unprimed and primed set of variables. So essentially we'll just have two sets of variables. We need the primed and unprimed because we'll have to add this r in. So t will be in terms of unprimed and s in terms of primed variables and so on. But at the end of the day, our frames will be always be in terms of this unprimed, the same set of unprimed variables, right? So whenever we add a clause to a frame, this clause is essentially going to be over this same set of unprimed variables. Similarly, whenever we block like a clause off from a frame, it is going to be over the same set of variables. So what we do in terms of sharing these clauses, and so that we can share the learn clauses within the same solver, is we'll have this set of activation variables, like we saw there for the example that I showed for the unsat code extraction, right? So we'll have this set of activation variables, and what we'll do is that we'll say that, okay, if the clause that we want to add in, we want to add it to the ith frame, then instead of adding just the clause to the solver, what we'll add to the solver is this constraint. If the ith frame is active, then this clause should be present, right? So every time you want to add a clause, yeah.
No.
Yeah. So every time we want to add a clause, we'll, instead of adding just the clause, we'll add the constraint. The activation variable with respect to that clause should imply this clause. So you guys just remember this part as well, right?
Yes.
Yeah, and whenever we check or whenever we want to basically add a particular clause, or we want to check with respect to a particular clause in our SAT check, all that we need to do is, instead of Ending the entire clause here, we'll just have to put the activation variable, because the constraints with respect to the clause are already there. So we already have in our solver. So if your frame fi is C1 and C2 and C3, we have in a solver something like f act I implies C1. All of these constraints are already in a solver, right? And whenever we do whenever say for a CTI check or any other check, we want to have as a part of the check fi, what we'll do is we'll have f act I as one of the assumptions that we are going to pass to this check function, right? Then whenever you pass this assumption in, what's going to happen immediately is that all of these constraints are going to be reduced to C1, C2, and C3. And so essentially your solver is now going to have a constraint that says C1 and C2 and C3, which is what your FI was initially, right? So this is how we're going to use a single solver to keep track of multiple frames and so on. So any question with respect to this? Yes, no, I think. Okay, so no questions. You guys can hear me, right?
Yeah.
Yeah. Okay.
We can.
Right. So now now there is this other so this is basically what we want to do in terms of the algorithm, or in terms of the implementation of this that we want to follow. And there are two optimizations mainly that is going on here. That one is the generalization. When we do find a CTI, we generalize this CTI, and when we don't find a CTI, we block a more general form of the C, like when of this S, right? So when we don't find a CTI from this S, we generalize this S and then we block that. So another slight modification that we can do to this is the following. See, when we actually find that okay, this S does not produce a CTI, we're doing this check with respect to FI, right? So we have, say, so if I draw a picture over here, say, or maybe let's go to our next slide. So we have our situation that we had before. We have the black region, the red region, and we have our incremental frames that we had. And as before, we have sort of we had this S point, and we have found that this S point is not a CTI, right? So there is nothing in the previous frame that also that in one step leads to this same S, right? And within what we did was we generalized this. So there is nothing over here that in one step leads to this point, and we generalize this to a region in some sense, a clause, such that there is nothing here that leads to anything inside this clause, right? And then we say that we'll block it off in this frame. Now imagine that there could have been this other even bigger frame, right? So if you remember, the situation is that in this bigger frame, we have already blocked off the fact that we're looking at this point with respect to, so let's number the frames. Let's say this is F0, F1, F2, F3, F4, right? The fact that we are looking at this particular S inside F3, so we are looking at S in F3. So the fact that we are looking at this situation and try to block or trying to see if S comes from a CTI for the inclusion of F2 into F3, right? Means that S itself was a CTI for something in F4, right? So there was some point in F4 that was itself a CTI, and we're trying to remove S from F3 because S led to that point in F4 that was a CTI, right? Now,
Yes.
yeah, so now that means that particular point in F4 would have been already been removed. So F4 would right now, if you look at the way that we are doing the algorithm, we maintain this fact that F4 always has or the previous frames always have this CTA is removed. So if you look at the algorithm or the pseudocode that I've written, whenever we do find a certain CTI, then we sort of immediately we add the next CTIs in, and we also immediately remove this, we block this CTI from every previous thing, right? Every frame that came before it. So this will be blocked off in F4. Now what we're going to do is we're going to say that in F3 we're instead of blocking this S, we're going to block this gray region S prime, right? And we are going to block this off in this way. So this is going to be our new F3 now. So far so good, but what can happen is we didn't have anything in F2 that could in one step lead to this this particular F3 here. But what we can sort of also check in some sense is that like this F3, we know it should also be blocked in F4, right? So this F3 will, or this S we know should also get blocked in F4. So we'll also be blocking this one like this when we block this S prime. But what may happen is that maybe this F2 frame actually had extended here, right? And then this S prime that we had gotten, if in this sort of a situation, this S prime still doesn't produce any CTIs. There is nothing inside F2 in particular that actually leads to something that leads to S or S prime. So there is nothing, no point in F2. So S prime, if you remember, we're looking at it with respect to F3, and there is nothing in F2 which in one step leads to S prime at all, or anything over here at all. So this, having this not blocked in F2 in some sense is not a CTI, because there's nothing, is not like wrong in some sense, because there's nothing in here that will lead to this in one step. But we can see that if we sort of do a search with this S prime with respect to F2, there aren't like anything. So all the points in over here are also unreachable from F1, right? So since there is nothing in F2 that can reach into this S prime region in a single step, you can essentially, and I mean, if you could check this and find that there's nothing in F1 as well that can also reach it here in a single step, what you can do is essentially, instead of blocking it in F3, you can also directly go ahead and block it in F2, right? So imagine this sort of a situation where you have, say, your previous figure, and you know that, okay, you've blocked this S prime in F3 and F4, and you know that there's nothing in F2 that in one step reaches here. But there could have been, say there's also nothing in F1 that in one step goes here, right? So what you can do is, instead of just blocking it in F3, you can also go ahead and directly block it in F2 and F1 as well, right? So let's imagine this sort of a situation where, say, we have these 4 frames again. And say that we actually have found some particular point here that was a CTI, and we try to, okay, so we found that this point is a CTI, and we try to block this. And while trying to block this, we find that, okay, this point was a CTI in F4, but when we try to block this in F4, when we try to propagate this forward and seeing if there is any CTI that leads to this, we find this large gray region. Let's say that this was our or let's say that when you try to find some point in F3 that leads to this particular S in F4, then we find this large gray region that actually intersects a lot of things, right? So what we have is this, we have this S that we initially gotten from the first CTI check in some sense, which is just checking whether anything in F4 in the last frame is reaching the red thing or not, right? And that's where we got our initial S, right? Now when we're trying to see for a next for whether this initial S comes from another CTI in F3, in some sense whether it's reachable from F3, we see that it's not, and we get this large gray region, right? So what you would normally do is you would just block this S in F4 or this gray region in F4, and then you would propagate this forward in some sense, or backward in some sense, right? But what this paper suggests doing is that they suggest to do a sort of a slightly stronger thing, which is that whenever you get this generalized region from the same SAT check, what you can find is that you can find the earliest or the smallest frame that actually intersects with your region here, this S region, and from the SAT check directly you can sort of block only up until that, right? So your normal procedure would have been this, where you gotten this region, and then you if you go to the pseudocode, this is the pseudocode that you had, right? And this is you have got in internalism, and we have extracted S prime from this unset code, and then from all the I to the K, we are actually blocking this S prime, right? So in our previous one, what we would have done is we have gotten this S prime in F4, and we would only block this entire gray region in F4 itself, right? So F4 would have become something like this. Right? And you would not have modified this F3, F2 or anything like that, right? So instead of doing this, what the paper says that, okay, from this unsat check itself, or the CTI sat check itself, what we can derive is that this generalized region actually intersects with all of like this F2, and we can actually block off this region in F2 and F3 as well, right? So we can, from the sat check, somehow find that this gray region intersects with F2 and F3, and we can block them off as well at the same time. So we can modify our F3 and our F2 to this sort of a situation. And so this will now be your situation. So you can directly block it off in F3 and F4, right? So previously what we were doing is that whenever we found this S, we are extracting this gray S prime from the unset core, and then we are blocking it off from whatever frame we are working on to the last frame, right? So we were going, this loop over here was going from the current I that we have to the last frame that we have, and we're blocking off this generalized S that we have gotten from the unset check in all of those frames, right? But what basically they suggest is that, okay, instead of going from the frame that you're currently at, you can actually start from a even earlier frame if you can derive the fact that, okay, even if you consider this S to be as a part of this earlier frame, this is still not a CTI, right? So or the fact that, okay, this particular S prime that you have is actually intersecting with this previous frames. So how can we do this? So firstly, is the sort of the conceptual idea of this clear as to why this can be better and why this is correct and so forth? Are there any questions?
Yeah, it's okay.
It's okay, right?
Yeah.
Yeah. Is it also clear that this is not necessary for correctness? Yes or no?
Look, do you explain about the correctness?
Come again, I can't hear you.
Can you explain about the correctness?
Yeah. So so what we were doing previously was correct. That's basically what I'm saying. So even if we don't do this, even if we don't block it in the previous frame, just blocking it in F4 onwards is correct, right?
Okay. Yeah. Okay.
Because you see all the things that we have in S prime are unreachable in any case, and so
Yes. Okay.
yeah, right. So your entire invariance for these frames will be satisfied in any case, right? If you have any frame, then the image of that will still be here, because all of those are unreachable in any case from F3. So the image of F3 will still be inside F4 in any case, right?
Yes. Okay.
Yeah. So right. So but blocking this is a good idea, because if you can, like as I said, the more clauses that you sort of block, the tighter your frames get, and the better the chance of you actually getting to a proof of inductiveness at some stage, right? So you want to block this in multiple different frames, and the way you can do this, and here is where crucially using a single solver becomes very beneficial. So yeah, up until now, whatever that we have done, we can use that. We could have done that by having multiple solvers in for one for each frame and so on. But here for this one, you need to use one single solver and this sort of activation variable framework. What you do is essentially, previously you could sort of imagine that your sat check, you could have done it by activating, say let's take this example from over here. So you would have activated the fourth frame by having f act 4 as an assumption. You would have your r t comma s, and you would have your particular things from your s1. Say your s is equal to x1 and x2 and not x3, let's say, or something. X1 and x2 and not x3 you would have had, right? And then from over here you would have gotten an unset core, and everything in here that was not in the unset core you could drop, and all of that you can do. But what we can do is essentially, instead of activating just the fourth frame, we activate all the frames coming before in them as well. So we activate f act 1 and f act 2 and f act 3 and f act 4 and so on, right? So whenever we do this, in some sense, what we can essentially wait. So I think yeah. So I think I've confused myself a little bit over here. Right. So essentially, whenever we activate all of these frames at the same time, what we want to do in some sense is check which of these frames are necessary towards getting this particular unset result, right? So if we can get this unset result by having like an older frame over here, then we would know that okay, that particular frame is sufficient for us to give sufficient for us to conclude that this is a CTI, right? So if we have multiple frames like this, and if we AND all of them together and say that we okay, so the only problem is that this sat check is actually looking for points in fi, and like it will activate all of these clauses and will look for points over here, right? That lead to it. So if say there is just one moment, I think I've confused myself. So if there is a point in f3 that is going to be here, then Yeah, okay. I think this is not exactly what we're doing. I'm extremely sorry. So, right. This yeah, okay. So I have completely messed this thing up entirely, and I really apologize for this. But so this is the part of the paper there where they talk about what I'm trying to talk about over here, and like here, as you can see that they're talking about some assumptions. I don't know if you can you see this what I have on my screen right now.
Yes, yes.
Yeah, so they're doing the there here is where they talk about the particular generalization for um generalizing this s to a particular s prime and so on, right? So in the unset case, for example, over here is what they say. So they're saying that they'll remove all the details of s whose corresponding assumption s prime was not used, and that they can get from the unset code, that we can get from the unset code. So this is what we're doing in any case to get the s prime from the s. And also notice that they have this act case, basically those effect i's that I was using. So they've also added this act k plus 1 to up until n plus 1 and so on. And they're saying that they're going to find the lowest acti that was used, and then it's going to return this thing. So what it seems that they're doing is basically so instead of adding the previous frames, they're actually adding the like activating the next frames and so on. And they are trying to find that the situation that okay, this new thing that we're blocking off over here, maybe the fact that this s is a point here is not necessary. We can actually use the fact that the s is a point in the in one of these like earlier frames. Okay, that actually makes sense. All right, sorry. So okay, I have completely messed this up. So I'll erase this. I'll delete this one. I'll actually put a line through here. Right. Sorry. So I had completely messed this up. I'll start over. So we have your frames. Right. And yeah, so let's say that we have this sort of a situation where we have a particular point over here that, or let's say even over here, that we know that this particular point has no CTI in the previous frame, right? And what we have done is that via the SAT check, we have generalized this to a region here. Now, what we can also extract from the SAT check, what they're doing is basically, what they're doing in that extraction is that we can ask this question, right? So in the SAT check, if you remember, our SAT check was that, okay, this point should belong to this particular frame, say F1, F2, F3, and F4. And our SAT check was basically trying to look for points in this frame F2 that goes to this particular, or let's say the points in this frame S2 that goes to this particular point S in F3, right? So then we would have blocked this off in this particular frame in F3. If we find that there are no points in F2 that goes to anything in this S prime, this gray S prime region, then would have blocked this S prime region off in S3. But if our SAT check also gives us that there is no point in F3 as well, let's say, that also goes to this same gray region, then we could have also directly blocked this S prime region in F4, right? Does that make sense? Am I making a mistake again?
Yes, yes.
That makes sense, right?
Yeah.
Yeah, so we could have also blocked this off in F4 if our SAT check also gives us the fact that there are no points in F3 as well that goes to this gray region, right? Similarly, if there was no point in F4 and if you had an F5 frame, then and there was no point in F4 that goes to this S region, we would have blocked it off in F4 as well, and so on, right? So in general, what we can see is that we can actually, like, instead of blocking it off at the F3 frame, we can actually take the, or in our case, this F3 is where we want to basically essentially block off this S prime. Instead of blocking it off in F3, F3 was before the block of procedure, F3 was this. We can actually look for something later on that we, or some frame later on that also has the property that if we block off this S prime, then no reachable states are being lost from this frame, right? So we can essentially block off this S prime in a later on frame as well because of this. If a SAT check gives us that, okay, we're not losing any reachable states if we block it off in F4 at some, if we block it off in some later frame, right? So essentially what we'll do in our SAT check is that, so remember that what we have is, so what we have given to us in this situation is this thing. We have our S, which is some x1 and x2 and so on up until some xi, let's say. And we have we are also checking, or let's call this J, and we're also checking at some particular frame. So we want to check for a point T in some particular frame, let's say Fi, right? So in our case, let's say this Fi was our F3. So previously what the SAT check we would have done is basically we would activate the expression F, or fact3. So fact3 would activate the constraints for the T variables corresponding to the frame F3. And we would say that R T comma S, and then we would say your X1 and X2 and up till Xj, right? But we also say that, okay, so what this stat check is looking for is basically it's looking for points in F3 that in one step lead to a particular, or let's say this sorry, it wasn't I was equal to 2 in our case, so I is equal to 2 in our case, so we'll block of F2, right? So we're looking for points in F2 that in one step would have led to some X. But we also say that, okay, we'll also actually allow for points in F3 to also be here, right? So we'll also activate F3, right? And we'll activate this F4 and so on. So we essentially activate all of these next frames and we look for a point in, so essentially what our stat check is now looking for is a point in any frame after F2, like any frame containing F2 in some sense, that in one step goes to our S region, right? So if we can find, so firstly, if we can find such a point, then we have a counterexample, or we have a CTI that we can work with. Otherwise, what we know is that, okay, if we cannot find such a point, then we look at which of these particular effects was actually used. So we look at the unset code and we see that, okay, which of these effects was actually used. So if we see that, say, for example, this effect 2 was not even used, right? So this was not used. So that means that even if you don't have this effect 2 as a part of your, or even if this these constraints with respect to F2 were not present, you would have still gotten your CTI, right? Similarly, if we see that F3 is not used, that means that, okay, if the constraint with respect to F3 was not present, you would have still gotten your lack of, sorry, you've still gotten the lack of your CTI. So from the unset code, we can look at what was the largest, what is the smallest I such that this effect I is used, and we can block off this S prime in that frame and all the future frames, right? So,
Okay.
yeah. Hello? Hello?
Yes.
Yeah, was there any question?
No. Okay.
Yeah. So notice one thing is that, firstly, usually our idea for the frames is that each frame contains the next one, right? So essentially, when we are activating all of these frames together, in some sense, this stat check is only looking for points in F2, right? Because with respect to F2, all of the constraints of F3 and F4 are in some sense redundant, right? So if we do find a point, we know that this point is going to be inside F2. So in the case where we do find a CTI, this same stat check actually works. Is this part clear?
Yes.
Yeah, right. But let's consider the case where we don't find this CTI and we want to block this S and so on. Then if we find that the unset code, we are actually using this effect2 in the unset code, this effect2 variable was actually important. That means that to make this a particular expression unsat, or we cannot say directly from the fact that this expression unsat that we can drop this. But let's say that this effect2 was not important, right? That means that we could have dropped this and we could have just said effect4 and effect3 and R and S. This thing will also be unsat, right? So if our unsat code of this particular expression does not contain this, if it does not contain this effect2, then if we did not have this particular expression would have also been unsat, right? But what is this stat check? This stat check is just looking for points in F3, right? Because again, with respect to F3, F4 and so on are redundant. So it's looking for points in F3 that in one step lead to our S, right? So that means that if this expression is unsat, that means that there is no point in F3 as well that leads in one step leads to this S, right? So then we can not only block it off in F3, but we can also block it off in F4, because if there's no point in F3 that in one step leads to S, then we can actually in some sense block it off in F4, because in F4 all of the things in S will be unreachable in F4, right? So in some sense, we're doing several CTI checks at once with this particular SAT check. And we are finding what is the highest level at which we can block off this particular S. So let me draw this picture once more to just make it clear. So we have again a black region. I should copy this because I'm drawing the same sort of thing several times. And we have many different frames here. And now the check that we're doing, or the situation that we have firstly, is that we have this S, and this was our F1, this is our F2, F3, and F4, right? So on. So the situation is that we have this S, and the first, like in some sense, our original SAT check, what it was looking for is it's going to look for points in F2 that in one step lead to S, right? And it has not found any points. So that means this S and the generalized S prime. So, and the generalized S prime, but let me not just so S and S prime, you can sort of think of them as interchangeably in this case. But if we don't find, if this original SAT check, if this original SAT check of that has just F at 2 and R and S, if this is unsat, then that means that there is no point over here. There is no such point here that actually in one step leads to S or S prime for that matter, right? But let's say that we also had and of F at 3 here. Now, if this is unsat, it still means that if there is no point in F2 that in one step can reach over here, correct? Because adding this F at 3 doesn't actually change what we are checking in this SAT check in some sense, because all the constraints of F at 3 are in some sense like redundant with respect to the constraints of F at 2, because F2 is in some sense contained in F3, right? So if you AND in all of the constraints in F at 3, you're not actually removing any points from the region that you're checking the satisfiability of. So this SAT check still says that there is no point in F2 that in one step leads to S. But if then of this SAT check, we find that this F at 2 is not in the unset code, then what that means is that this SAT check, we know directly from looking at the unset code, is that this one would also have been unsat, right? Now notice what this SAT check is telling you. F at 3 and R and S is unsat. What this is telling you is that there is no point in F3. There is no point in F3 that leads to in one step in S, right?
Yes,
so that, yeah. So that means that you can not only remove your S in F3, but you can also remove it in F4, correct?
yes.
Okay. I think Amin dropped off and joined back, right? Are you there? Hello?
I think Amin has some internet issues.
Right, okay. Yeah, so this means that
He just messaged, he had a power cut.
yeah, what is the dot? Is it in the chat? Because I can't see the chat window at all.
He messaged me on
just-
Telegram.
Okay, right. So can you tell me what the doubt is?
No, he doesn't have it. He just said he had a power cut.
Oh, he sent a power cut. Okay, sorry. I think I misheard you. Sorry. Yeah. Yeah. So yeah, so if you can in some sense drop this effective from the SAT check, what this means is there's no point in F3 as well that can lead to this thing, and you can actually safely remove this S prime region from F4 as well, right? So by adding this extra F at 3, and you can do the similar thing for F at 4 as well, although since F at 4 is the last frame, it doesn't really make sense here, because I mean if there's nothing in this last frame that can reach from that in one step goes to something inside S prime, that really doesn't let you do anything further, right? But the idea is that if you can sort of, if you sort of add your next frame's activation constraints in your sat check, what that allows you to do is that it allows you to look at the unsat core and see that if you can drop some of your frame constraints and still get an unsat expression. And that will basically tell you that, okay, are there points in not just in the frame that I'm trying to see, are there any CTIs in the frame that I'm trying to see, but it'll also tell you, are there any CTIs in any next frame that you're not looking at currently, right? And so you can basically block off your S prime in higher frames as well, right? So in some sense, so does this sort of optimization make sense? Also note, also note that if you do get a CTI, for example, over here, say you're doing this sat check and you do get a CTI, let's say you're doing this, you're looking at this S, and you're doing this sort of a this particular sat check that we have, this sat check, and you do get a CTI, right? So you get, let's say, so you get some T that actually satisfies this expression. Note that then that means that this T actually satisfies all the constraints with respect to effect 4 and effect 3 and effect 2, right? So that means that this T that you would get from this sat check, if this does become sat, then you would get this T. If this does become sat, then this T that you get, this T will actually belong to F2, right? Because it satisfies all the constraints with respect to the frame F2, right? So if this sat check is sat, then you're actually going to get a point in F2. So it's by adding this extra constraints in, you're not actually, you're not messing up the sat case of this sat check at all. But when you get the unsat, then you can actually, since you have these extra frame like activation variables added in, you can use them to sort of discard some frames from where you don't need to block this particular expression, and you can actually block this S in some higher frame, right? So this is clear, right? Hello?
Yes, sir.
Yeah, okay. So let's get the pseudocode and modify this slightly so that it now reflects this thing as well. Right. So previously what we were doing is that we are doing this sat check, and now our CTI sat check has actually been modified somewhat. So let's actually write down in our pseudocode what our CTI sat check is. So our CTI sat check is going to be we're going to have all our frame activation variables from I up until L, right? So FL, if sat check, so FL and FL minus 1 and so on up until your FI, and you have your R, and you have this, all of the clauses or all of the terms of your S, right? So this is a CTI sat check now, and if this is actually sat, then we don't change anything, right? We do exactly what we were doing previously, because if this is sat, then it still means that we have a particular, so we have some T that is in the frame I minus 1 that we need to block in I minus 1 and so on. This will actually be I minus 1, I think, if I'm getting the indexing correct. So if this is sat, then we don't need to check change anything. But if this is unsat, then what we do is we actually pop this from the queue and we extract this S prime from sat core. We also do another step here, is that we check find largest j, or sorry, find smallest j, so that if j is in sat core, right? And then instead of blocking this S prime in everything, what we'll do is that we'll just block it from j up until the end, correct? Because so if you remember, if you have the situation where your S prime, this is your S prime, let's say, and then say that this S prime is actually unreachable from this one, then or there is nothing in this particular frame that in F3 as well that can in one step lead you to S prime. So then you can directly just block it in F4 and just sort of call it a day, right? So you don't need to worry about blocking S prime in anything previously before F4 and so on. So, okay, so I think again, to get the indexing right, it should be j plus 1, if I'm not getting it wrong, because in the other situation, you would have gotten I minus 1 from this j here, and then you would want to go from j plus 1 to this. So you can actually avoid blocking it in any of these particular frames where it doesn't matter, right? So if you can drop a particular frame, let's say that if you can drop this the assumption of this F2 and still get an unsat thing from this one, then that means that there is nothing in F3 that can go here, and then you can directly just block it in F4, and you don't need to worry about blocking it in F3 at all, right? So in some sense, you're blocking it at an earlier or at a later stage of your thing, which will correspond to earlier in this backtracking process where we are looking for, where we are backtracking from this red region to look for counter-hexagonal path to the black region, right? So essentially, then you would change your, in this situation where this is also unsat, you would change your F4 to look like something like this. F4 would have it blocked. And since there's nothing in F3 that in one step reaches to here, then F3 image is also contained in F4, and everything is fine, right? So yeah. Wait, why is this G plus 1? So is this last bit of optimization clear? Hello?
Yeah, hello.
Yeah.
Can you hear me?
Yeah.
Yeah. Yeah, like I missed half of the stuff. Like I had some internet issues.
Okay. Yeah.
So
So okay, I'll quickly
I'm not
just,
sure of what happened, but I'll just I'll watch the recording once more. I think that would be better.
Sure. And let me know if you have any questions. But essentially, what I suggested is this another bit of optimization that we can do is that we can actually, instead of blocking S prime at this particular frame, we can block it at an early or at a later frame, and not worry about blocking it at some earlier stage, right? So if you block it at a later stage, then we can hopefully block more potential counterexample search paths, right?
So by later you mean we are blocking it at like the higher number, like
higher number, yeah.
Yeah. Okay. Yeah. So, okay.
Yeah.
Yeah, I'll just like watch it once because most of the stuff like I had internet issues, then I had a power cut also. So like I couldn't
Yeah,
hear most
sure.
of the stuff. Yeah. Okay.
Yeah. So just to like recap, the gist is basically instead of doing the original stat check, you also add in the constraints for your later frames, higher number frames in your stat check, and then you get the unsat code. And if the unsat code tells you that you can drop in some of the constraints of the lower number frames, then you know that there is no point in your lower number frames that can actually reach to this S or S prime region in one step. So you can block this S prime region in your higher number frames. So essentially you can, so if you add, so instead of just checking for a point in F2 that in one step reaches the point in S, you're checking for a point in F2 and F3 and F4, which is just F2 that in one step can reach to a point in S, and that turns out to be unsat. So there's no point in F2 that can reach to one step to something in S. But it also turns out that from the sat check that you find that, okay, this constraint at this point was in F2 was unnecessary. We could have just relaxed this constraint to saying that this point is in F3. So that means that there's no point in F3 that can also reach in S in one step. So we can just block this entire S region at F4 and be done with it. Right?
Yeah, I get it.
So that is all that we're doing. Right. And notice that since
for that we are doing the unsat core thing, right? Like
that we are doing the unsat code.
yeah.
So I'll give a short code demo of how unsat code works in Z3 because you guys asked for that last time. But yeah, so notice that since we're doing this queue-based thing, if you actually block this off at some higher frame number, then whenever you're looking for this more propagation, like more CTIs to look for, you're actually going to, in some sense, so if this is blocked off in some higher number, then so say if it is blocked off in F4, you're going to actually find, like when you're looking for more and more CTAs, when you're doing this exhaustive search for CTAs in some sense, you're going to, like if you had blocked it off in F3, it was possible that you would have actually found something in S again that was inside F4 and not in F3. So if you're instead of blocking off in F4, if you had blocked it off in, say if your situation instead of this, if it looked like something like F4 is still your original whatever it was, and F3 is actually what you have modified. So if your situation was this now and F4 is this, then it was possible that in this iteratively looking for CTIs, you would have actually found this is a CTI again, and then you would have had to block it off in F4 again, right? So we avoid this by directly blocking it off at F4 by looking at the the unsat core and adding in the extra constraint of F3 and seeing that, okay, this point that we're looking for, it may not have been in F2, it could have been in F3 as well, but we still wouldn't have found any such point.
Okay, yeah. So like it would reduce the number of CTA searches, right?
Yeah, it would reduce the number of CTA searches, and the paper says that it does reduce it very largely. Like if you think about this, it is in some sense, if you sort of imagine the CTA search operation as being this exponential backtracking from this red region, then you're blocking off this huge part of the space that you have to backtrack over here. You're just blocking it off over here by blocking it off early, right? So this, the paper claims, is going to be an exponential improvement, and the experiments suggest that it is an exponential improvement by blocking it off at some earlier point. So
okay,
yeah. So right. So yeah. So this is it. Now this is this Eurocode, and this is just the CTI check part that has changed. All the rest of the thing is basically exactly as Sir said. So it is just remove CTI that has changed. Everything else remains exactly the same. Of course, there's some framework changes in the sense that we are representing our frame FIs within the same solver by adding clauses in them as FI implies some clause. And if you remember, you also had to track the clauses in your FIs in some list so that you can do the propagate clauses. And there is all of that that code that you'd have to write. But yeah, as far as the remove CTI is where all the optimizations come in, and that is given in this particular pseudocode, right? So
Could you also upload these slides in the page, Moodle page?
yeah, I'll do that. Yeah.
Yeah. Okay.
Yeah. So yeah. Okay. I think there's one slight error here which I've made, which is that I think this particular blocking will be from this L is from 0 to I. It will not be from 0 to I. It will be from I to the end. Let's call that capital N. And similarly over here, it will be this L is from I to N, right? Because this particular loop is basically when we have found this generalized T and we're blocking it, then we want to block it in here and all the future ones as well, right? So this is from I to N. That's correct, right? So because when we have found a particular, so let me just draw over here, I guess. So if say we have this sort of a situation and we were looking at this S here and we have found a T over here that in one step goes to this S, right? So if we do have found a T, we want to remove this particular, so we want to look for anything in the previous frame that leads to here. But before we do that, we want to sort of remove this from this particular frame, right? So we want to remove this from, so which is what we're doing in the original one as well. So we want to remove this from this particular frame. And then in some sense we have this S was already removed from this particular frame. So this had already happened previously, this removal of this S. And this would be a situation right now. So yeah. So this particular loop will actually not be there, and all we'll block it in is this particular FI, right? So we block it in FI. And the situation where we have found a particular J that we want to block at some earlier stage, there we actually block. So say that we want to block this at some earlier stage, then there will actually block from here to the end onwards. So we block from 0 to J plus 1. So does this make sense? Is the mistake that I made, like, or at least is this corrected version, does it seem correct to you guys? Because I just like made a mistake there, I should think we should all verify this, right?
Yeah, I think so.
Yeah, because if you look at the situation where we are having just a single thing, this T, and we have not explored, or we have not done this SAT check to check whether there's something else that is reachable here, but we know the T goes to something in this S, then we have to remove this from this current frame. So this is our FI in some sense. We have to remove this from T from this current frame. But I mean, we could remove this from these next frames as well, but that is strictly like not necessary in some sense. Because yeah, I mean, if this T, if there was something in this Fi that does, or something over here that does lead to this T, then in some sense we would have removed that as well, and so on. So I think removing it from here, and since we have removed it from here, removing it from this next frames would also have been safe, but this is fine. So yeah, we can just remove it from this particular frame here. And if we find that there is no such T for a particular S, so in the other picture, if we have this and we find that there is so say we have, this is our S now, or let's just say that we have our S in this now. You know, let's say that we have, this is our S, right? And we find that there is no T that actually comes from here to S. So then we block this S here, and we also block it from in any of these smaller ones as well, right? Because it might have been that while we're looking at S with respect to this Fi, S might have also been a member of some lower frames, right? So there might have been another frame like this over here. And we don't want to just remove this S in Fi, we want to remove this in S in all of these previous frames as well. So we'll have to, over here, we'll have to block it in all of the previous frames. So this loop over here is actually necessary, right? Where we block it, not just block this unreachable thing, not just in this current frame, but also on the lower number frames, right? Because if it is unreachable, or if you've just proved this particular point to be unreachable, and if it is in the current frame, it might be that it is in these lower number frames, and we should block it over there as well. But we don't need to, in some sense, block it in the higher number frames, because or that may not necessarily be correct as well, because in the higher number frames, the invariant is that anything that we're coming from the lower number frames should be, or anything in Fi plus 1 or Fi that via one step should be there in Fi plus 1, right? So even though we have blocked it off, we can't directly block it off in the Fi plus 1 frame, because there might be things in Fi that in one step goes to over there, and we are blocking off something in the higher number frame where we might lose some things that are reachable in the higher number frame from Fi in that sense, or in that situation, right? So here we want to go from 0 to j plus 1. So we want to block it off in the lower frames, and there we can just block it off in the ith frame. Is that okay? Does that seem correct to you?
Yes. I think so.
Right. Yeah. So then this particular optimization, where it looks at multiple frames at the same time, what it will do is, say if it finds that there is nothing in F3 that in one step reaches over here, it will block it, this S off in F4, and then it will go ahead and block it off in F3 as well. In this loop, and F2 and so on. And we'll of course do this redundancy checks where we see that, okay, is blocking it off in F2 actually removing any points at all, and so on, while we are blocking things off. But yeah, we'll have to do it in, we'll have to block it off in F4, and then in F3, and then in F2, and so on. So right. So this is clear, right? I mean, this also seems correct to you as well. I mean, I don't know if you're following much, but the fact that that we'll have to, if we find some S that is unreachable, we'll have to block it off in that frame and all of the lower numbered frames, right?
Yeah, then only like we can see whether it's like. God, no. Yeah, I get it. I get it.
Yeah, that is correct, right? Okay, yeah, sure. So okay, so this is the all of the optimizations and things about the implementation of the PDR that you guys will be doing. So are there any questions as in any high level or anything like that? You can also mail me any question, because I think a lot of this is becoming like both Amin and Ratnakar will have to go through the videos once before they have. Maybe then they'll have a
Yeah. If I have something like, I'll mail you anyway. I think
Yeah.
during the implementation we will have many doubts.
Yeah, definitely, yeah, and we'll do mails, and if you want at that point also, I can like have some sessions.
Hey, one question I had. Okay, one actually a request. I mean, how you, between the three of you, just decide yourself as to what, how you apportion the work. Okay, which modules that you will be actually coding for. I'm hoping that you will, or how you distribute the work. Okay.
Yeah.
Yeah. Like we have not discussed about that
I
yet.
think that what I'm asking you is to discuss and then decide.
Yeah. Like right now, Ratnagar as an example.
Yeah, to make sure that each of you has contributed equitably.
Yeah, like anyway, all of us should put some work. Otherwise, I don't think we could finish it also. So
Yeah, this is like enough work for 3 people. So I mean, I can give you some briefs, a sort of a dependency chart or something like that for the code that you need to write. So one of the core things is this. So you'll have the frame manager, right? So this what this will do is basically this will keep track of the number of all the clauses in your frame, and it will implement your particular block methods, right? So whenever I'm saying, this is block method is basically whenever I'm saying f is f and something, this is basically what I mean by this block method. So it will implement those, right? So this you'll have to basically get done fast, and this will not be much work, because this is just this keeping track of all the clauses. This block method will just add a clause, and keeping track of all the clauses would be basically you just have your solver, and you whenever you want to add a clause in your block method, you do this add fact I implies that clause is a constraint to your solver, and you add your clause to the list of clauses, right? So this will have to be I mean, this is work for one person, but if you can like discuss and maybe get this done quickly, that will be good, because this is like everything else will depend on this in some sense. Then you have mainly 2 or 3 things, right? So you have one part is this propagate clauses. So what that should do is basically take a frame, and it should given a frame, it should find all the relatively inductive things, and then from there it should it should call block for the next frames and so on. And then you have your the remove CTI function, and inside the remove CTI, okay, so the remove CTI function actually has this sat check and all of that is going on. So here we can sort of abstract out this ternary sim as a separate function. Then someone else can do this while you leave space for doing the ternary sim, and you do the remove CTA without the ternary sim, and then someone else can do this ternary sim part, and then you can just add a call to that function over here. So essentially you have your remove CTA, and that will have to do this SAT check and unsat core management. So remove CTI without ternary sim. And the ternary sim actually technically doesn't depend on the frame management. The ternary sim is something separate that you can actually, so you have just ternary sim over here. Yeah, and then you'll have to combine all of this. So you have your these functions over here, right? So your propagate clauses and remove CTAs are at this point done. And extend frontier is just it's fairly easy. So but like someone will have to do it, and you'll have your final PDR loop, right? So then you have the extend frontier can also actually be done once you have the frame manager in place. So once you have this frame manager in place, you can do three things. You can do your the propagate clauses, you can do remove CTI, and you can do extend frontier. And parallelly, you can do the ternary sim. And once all of these are done, you can actually write your final PTL loop. Right? So I think this might be a good sort of division of labor. I mean, and then you can, but you can discuss among ourselves if you want to do it somewhat differently. And this is just some basic idea that I have in mind. It might be better to do it differently as well. You can think of that, right? So yeah, maybe you can use sort of, yeah, like you can discuss among yourselves whether you think this is a good way to split this, to split the work, or anything else is better. Okay, so now I'll give a short demo of the unsat core extraction from Z3. So I'll do that inside this thing. So firstly, any questions up until this point? Anything that you want to ask or add or anything?
Yeah, nothing from me.
Yeah, I did like mess up a little bit over here today, quite a bit. Was it all clear at the end, or is it still somewhat messy?
Yeah, I got the basic idea. So like I'll just watch it once, then
Yeah, I'll also,
yes.
yeah, sure. Okay, so watch it once. Yeah. So yeah, so let me go to the demo over here. Right. So can you guys see the font? Is the font size okay?
Yeah, yes.
Alright. So right. So what we're going to do is let's create a solver firstly. And so the idea with the unsat core is that once you have a bunch of constraints added to your solver, you can, while you're passing it to while you're calling the check, you can actually add in a bunch of assumptions. And then the unsat core is going to be a list of which of these assumptions was actually necessary to reach the unsat result, right? So let's say that, so let's get some variables. So let's say v0, v1, v2 is our booleans. Okay, so I think fine. So we'll do it separately. I thought I saw a code of this particular style some point somewhere.
Yeah, like we could do multiple ones.
Yeah,
I'm not
how
sure why
exactly
it's not
though?
working.
Inside,
I'm not sure. Like
yeah, I mean, I thought
I
that.
can't remember it right now.
Yeah, I also thought that this something like this works, but apparently it doesn't. I mean, you could do z3.bool v0, z3.bool v1, and so on, but yeah.
No, like because in the first assignment I did like just
Right.
initialized 3 or 4 together or something.
Yeah, and I mean, I saw this. I think I've also used this style of code somewhere as well, but I also cannot remember right now. But yeah, in any case, we have 3 variables. So let's do s.check, and let's say that we'll pass v0 not of. Okay.
I think it was bools or something. Yeah.
Oh, okay. I see. Okay. Well, okay. I mean, fine. So we'll say that v0 not of, or let's say that v1 implies this is the syntax for implies, right? Or okay, no. Let's do v1 equivalent to v0, and then we do not of v1, and then we say that okay, v2, right? Or z3 dot not. This is unsat. Now, if you get the unsat core, so it says that v0 v1 equivalent to v0 and not of v1 is the unsat core, right? So whatever you pass to s, so when you s.check, you can pass a bunch of assumptions, and assumptions actually can be any sort of z3 expression. So whatever z3 expressions you pass to s, it will unsat core is basically going to return the minimal set. Okay, it may or may not be minimal, but a subset of these expressions such that this is also unsat, right? So this dot check will also be unsat. As you see, z3 has actually dropped v2 because, I mean, of course, if you just have this much, then this is unsat, right? So this is basically how you generate and use unsat cores. But as you see, if you look at what the unsat core actually returns, so let's say that L equal to s dot unsat core. And if you look at the type of L0, for example, so this is actually a Boolean reference in type of L1. This is also Boolean reference in type of L2 is also Boolean reference, right? So these are some internal Z3 types, and usually these correspond to various ASTs and things like that. So boolref is basically whatever Z3 returns to, like, whatever the type of Z inside Z3 is for a Boolean expression, right? So V0 is a boolref, V1 equal to V2 is a boolref, not of V1 is a boolref. V2 is probably also a boolref. But the point is that this is some internal type that this has, right? It is not like it's not returning indices of which constraints are needed and which are not, or anything like that, right? So to actually use this properly, what I would suggest is that because if you want to say that if you want to print L0, you get this. But if you want to check whether, say that L0 or a particular expression that you have returned, whether this is equal to a particular way, like which constraint does it have. So to do that, you'll have to basically do either an equality check or anything like that. So if you, since it's returning these Boolean references, you can't easily just do an equality check, right? Because if you do something like, for example, if you do this, it returns this, right? And if you look at the type of this, it doesn't return true. It returns actually just this. This is also a Boolean reference, right? So essentially, the things that you get from this unset code, you can't directly just compare it with whatever you have stored, and you can't hope to get true or false or anything like that from there. So what you will have to do is you'll have to use is, and that has some related issues, right? So if you do this, it has false, right? So sorry. So if you look at what they're doing over here, okay, it's actually, so if we do this, for example, right? So to check, for example, say if you had three constraints v0, v1 equal to v0 and z3 not v1, and so four constraints. So if you want to check, for example, whether these four constraints are in your S, right? And let's say that your constraints were something more complicated. Let's say that your constraints were v0, v1 equal to v0, z3. So the first three, let's keep them to be the same. And let's make this one a little bit more complicated. Let's say that this one is equal to v2 is equal to not of, okay, z3 dot not of z3 dot or of or let's say z3 dot and of v0 and v1, and okay, let's make this z3 dot or, right? And now if you go look at the unset core, right, it's still these three things, but it say you wanted to check whether this entire thing is going to be inside your unset core or not, right? So you can't actually store it in some variable and check whether that is in your thing, in your unset core. So what you need to do is essentially you would have like to sort of, in some sense, recreate this entire expression to check whether it's in unset core or not. And then you have to check whether it is in your s.unset core. Okay, I'm calling unset core again, but of course you can keep the list over here. And as you can see, what happens here is that this entire thing, okay, I think I could probably put a bracket here. Yeah, so this entire thing needs to be reconstructed to check whether it's in unset core. So if you wanted to say if you wanted to sort of keep this as an expression x, let's say, and then you do x in s.unset core. Yeah, so if you want to check whether something is unset core or not, you would have to carry around this whole huge z3 expression inside x, right? So in our case, what we wanted to check whether something was in unset core or not was or in general, when you're using unset core, if you want to check whether a huge complicated expression is in unset core or not, you basically have two choices. One is that you can actually keep this huge expression in a particular variable x, and keep carrying this variable around and checking whether this is in unset core or not. And that is expensive because often these like references to these expressions are actually fairly heavy. Like Z3 does some internal manipulation of ASTs, which makes this X variable is actually a reference into an AST. And that is stored in some more expanded and somewhat simplified form inside internally. And that often takes up some amount of memory. So this is relatively inefficient. What you could do, which is more efficient, is instead you could have like activation variables in a similar sense as to what we discussed previously for each one of your constraints. So you could say that, okay, we're going to have P0 is going to be Z3 dot. So you said it was bools, right? So let's try this. P0, P1, P2, P3. And so let's see, okay, this guy actually, yeah, okay. So, and this is the space. P1, P2, P3. So for 4 constraints, we have 4 activation variables. And then we see that, okay, we'll add to S P0 implies our first constraint. P1 implies our second one. P2 will imply our third one. Okay, Z3 dot. Oops. Yeah, and P4 is finally going to imply, sorry, P3 is going to imply our fourth one, which is going to be this huge thing. Right. Yeah. So now if you look at what your solver has your constraints guarded by these activation variables. And then you can do s dot check and you can activate all of them. Right. And then when you do s dot unset core, what you get is basically just a list of which activation variables are involved, right? So now when you want to check whether something is in here or not, all you need to carry around is this activation variables, which does not have a huge AST referenced behind them. So all, in some sense, all of the memory that is required for carrying around this huge expression is no longer being hogged by you in any sense. Because when you do this line, see, this entire expression is being created here, but it is being created as a temporary value. And then it's being immediately combined with this, and then this entire temporary value is being added, right? So then internally Z3 basically converts this to whatever form it needs to add it to the solver. So which is probably going to be some CNF form, and it's going to probably add it as a bunch of clauses to the solver. And then it basically will discard this entire temporary expression that you had created. So that will immediately free up a lot of memory. If you had carried this entire expression around, not only do you have the CNF clauses inside your solver, but you also have the AST representation of this entire expression. So that is basically keeping the same thing twice in memory. So it is more memory efficient in some sense to just have these guard variables and then to just do P0 in s dot unset code, right? Yeah. So this is how you essentially use this unset code. So are there any questions? Sorry. Hello, are you guys there or?
No, no, nothing from.
Yeah, okay. So is everything clear? Yeah, this is all I had.
Yes, yeah.
Yeah, okay. Okay, so yeah, this is all I had.
Okay, so
So I'll stop sharing.
yeah, I mean,